Welcome to today's podcast on polymer characterization. My name is Ray Chen, and I'm the applications manager of the spectroscopy business at Thermo Fisher Scientific. With me today are three technical experts from Arkema Inc., Dana Garcia, Sarah Reno, and Pierre Rico, as well as two of my Thermo colleagues, Steve Post and Chris Schaefer. Welcome, everyone. So let's start off with an introduction of yourself, starting from Dana.
So my name is Dana Garcia. I have a PhD in chemistry. I've been working with Arkema for 33 years, and currently my responsibility is the vibrational spectroscopy lab, encompassing infrared, Raman, near infrared, and also collaboration with the rheology lab on hyphenated techniques.
Thanks, Dana.
Hello, everyone. My name is Sarah Reno, and I'm a research scientist at Arkema. I work together with Dana, Pierre, and another 20 scientists in the polymer characterization group. My area of expertise at Arkema is more rheology and processing areas. My background, I'm PhD in material science with some background in ceramic composite as well and nanomaterials. So I'm really enjoying the collaborative work at the company. I've been here for 8 years now.
All right. Thanks, Sarah.
Hello, I'm Pierre Rico. My responsibilities at Arkema involve the X-ray lab areas that involve many different techniques from diffraction to elemental analysis to surface analysis. And I'm also in charge of the ICP-MS lab for elemental analysis aspect. My training is essentially in material science and physical chemistry. I did all my schooling in France and then moved to the US, and I've been now with Arkema for about 20 years.
All right. Thanks, Pierre. Steve?
My name is Steve Post. I'm the Business Development Manager for the Material Characterization Group at Thermo Fisher. The Material Characterization Group is responsible for the extrusion and rheology products from Thermo, which encompasses the pharmaceutical industry, food, material science, and what we'll talk about today, the polymer science.
Hello, my name is Chris Schaefer. I am Steve's counterpart in business development for what we call bulk elemental analysis. This group encompasses XRF, XRD, and optical emission. We are mostly focused in the industrial markets and the academic markets. I started with Thermo 13 years ago as an application specialist, went to become product manager in Europe, and now back in the US as business development manager for our group here.
All right, thanks. And again, welcome everyone. Let me give a very brief introduction about Arkema Inc. before we move into a more technical discussion. As you know, Arkema is a global corporation and a world-class producer of specialty materials, including acrylic monomers, adhesives, emulsion system, fluorochemicals, fluoropolymers, functional additives, and so on. So the group is structured into three segments dedicated to specialty materials: adhesive solutions, advanced materials, and coating solutions. Arkema Inc.'s Corporate Research and Development Center is headquartered in King of Prussia, Pennsylvania. It is responsible for research and development in the Americas and coordinate research and development activity between the U.S. and Arkema Research and Development in France and Asia. So all three experts came from, the polymer characterization group. Maybe, one of you can give us a high-level overview about this group. What is this group? What does this group do? And what kind of techniques are available in this group? What type of analyses you guys do on a regular basis?
So the Polymer Characterization Group is part of the Analytical and System Research Group department in Arkema at King of Prussia. And we use a large number of technologies to identify and characterize polymers in terms of structure, molecular weight distribution, morphology, and processing. So within the group, we have a number of spectroscopic characterization techniques: infrared, Raman, near-infrared, NMR, X-ray techniques, XRF, XRD, XPS, microscopy, optical, AFM, and also SEM with an EDX detector. We also have extensive thermal analysis capabilities, rheological, and microprocessing. Additionally, within the department, we also have GC, LC, MS, ICP, and GPC capabilities, which can be used for polymer characterization as well as small molecules. So most of what we do is identification and characterization of products and development targets, as well as extensive customer support.
All right. Yeah, no, that's, it's just amazing how many techniques, are in your toolbox, right? We all know polymer characterization is such an encompassing categorization, really depending on the analytical objectives, whether it's molecular mass, the molecular weight distribution, molecular structure elucidation, morphology, thermal properties, or mechanical properties. So it's really a wide range of analytical techniques, at your disposal. So Dana, if you don't mind, let me start with you and spend a few minutes on the vibrational spectroscopy. The characterization often has a goal to improve the performance of the material, such as strength, impermeability, thermal stability, optical properties, and the list goes on and on. So can you give us some examples how vibrational spectroscopy, whether it's qualitative analysis or quantitative analysis, and whether it's through FTIR or Raman or near-infrared, can be linked to the material properties?
So we use vibrational spectroscopy as a first indication on material identity and composition. This is important as properties are in direct consequence of structure, and vibrational spectroscopy is especially suited for both QC methods because of minimal sample prep and ease of use. So we can look at copolymers and blends and correlate that to properties, mechanical, thermal stability, processing. It's also an excellent technique to differentiate products and provide answers within a couple of minutes. It's probably the first technique that one uses when an unknown is brought to the department for analysis. So both IR and Raman are very sensitive to the presence of additives, so we can look at the lubricants, antioxidants, co-stabilizers. So you get an entire picture of what the material is within a couple of minutes, and then you can forward the sample to other laboratories depending on what the other structural or property information is required. So in a triage type environment, the vibrational spectroscopy lab is the first lab where the quote unquote patient is delivered.
Oh, yeah, that's an interesting analogy. You use the term triage. I think the part of the appeal or attractiveness of vibrational technique, it's a wealth of structure information, but also easy of use, relative simple sample prep. So it's interesting. You mentioned this is your first technique for unknown sample coming into the workflow, right? But you also mentioned early on that you have multiple vibrational techniques there. You have FTIR spectrometer, you have FTIR microscope, Raman, and a near-infrared in your lab. Can you give us a sense, maybe through some examples, if possible, on how each technique fits into that workflow? Or maybe, how do you pick? Where do you start? Based on what you make that decision, this is the right technique.
So the first thing is to look at two aspects. What is a sample and what question is being asked? So if you have a large sample, meaning grams or centimeters and above, we will start with FTIR and probably do an ATR experiment. This is the fastest and easier way to analyze and provides a first level answer on the structure. Sometimes you get enough of an answer that it does not necessitate to do additional techniques, or it may point that other techniques may be needed. On the other hand, if the sample is very small, like a defect, then the choice is between the IR and Raman microscopes. If the sample is not pigmented and we don't believe it will fluoresce, then we'll probably use the Raman microscopy because it's easier to prep the sample for Raman than it is for infrared. And it's also faster. Conversely, the drawback is that Raman libraries are not as extensive as infrared libraries, so sometimes there's a challenge in identification. If the sample is pigmented or we believe it will fluoresce, then we use the infrared microscope. And the technique we are going to use on the IR microscope, again, is dictated by the sample. If we can do a transmission measurement, that's probably one of the easier approaches, but we can also do micro ATR and micro reflectance. It's all a question of the amount of sample prep that is required. Most of what we do in those cases is material identification. What is the defect? Can you infer its origin? Is it something that potentially contaminated the product? And at which stage the contamination occurred? So there's a lot of information that can be obtained from just a couple of simple experiments. We work very closely, if we do either IR or Raman microscopy, with the SEM microscopy lab in terms of correlating SEM EDX results with infrared/Raman results, as well as the optical microscopy part to visualize what the sample looks like, which in many cases will provide information on defect identification and corroborate what you get from the IR or the Raman analysis. If it's a large sample and it's a product that has been calibrated for composition, then we can use both IR and NIR to determine that the composition is within specifications. We will tend to use Raman less in terms of a quantitative method and more as a qualitative analysis. So I hope that this gives you a flavor of the type of things that we do in the vibrational lab at Arkema, King of Prussia.
Yeah, absolutely. That's a lot of information, to say the least. Right? You look at your workflow, you're starting with the objective. What are you looking for? Then between techniques, you also compare, FTIR and a Raman microscopy. For example, the possible fluorescence for some of the sample will drive you towards FTIR microscopy as opposed to Raman microscopy. But you also said, you work with, optical microscopy, the SEM, and based on the information you can extract from those analyses, that will also give you a hint, which direction you want to go. So that's absolutely a lot of information. It's very interesting. You mentioned that, one of the most important application area for both FTIR Raman and microscopy technique is material identification through library search, right? You commented that, you would prefer, FTIR in a lot of cases because the library of FTIR is probably more extensive than Raman. Can you maybe comment on any software features that you found that's particularly useful to facilitate, library search?
I think what is important, besides having large libraries that encompass many compounds/products, is the importance of the software being flexible and incorporating multiple search algorithms, being able to do searches in second derivative, using chemometrics methods such as principal component analysis, looking at both the loading spectra and the score information, the ease of creating your own libraries and adding standards to your libraries, and the availability of continually improving libraries that one can purchase with updates and additional compounds included, compounds and products. Because there's a lot of information that one can obtain by identifying within the product space. You don't necessarily need to have a compound being identified.
No, absolutely. I agree with you. I think what you mentioned, for example, flexibility, right? To add build your own library, multiple search algorithm that allow you, to correctly or semi-quantitative assess, your search results, and some chemometrics capability. Those are important features. So maybe one more question on the vibrational side. So you mentioned both qualitative and quantitative analysis, and especially, you mentioned the compositional analysis. So we know, unlike FTIR and Raman, where you often have very defined features in the spectrum, near infrared, often has a broad overlapping overtone and a combination bands. As such, it is often associated with some chemometrics modeling, as you mentioned earlier, such as partial least square, regression, principal component analysis. Can you give us, maybe an example how near infrared, are used in your work for quantitative analysis, for example?
So we use NIR quite extensively, both in the R&D lab as well as in the plant QC labs. And the main driver is the ease of performing the analysis. It usually takes from half an hour to 1 hour to train chemists and operators to run the analysis. There's really no sample prep, at least in the polymer environment. We use powders. All you have to do is load your vials and run. We use pellets. You can put the pellets in vials or the rotating cup. It's actually less than a 5-minute operation. So we determine moisture and composition and additive loading. We can provide, if it's in the QC at the plant, they provide basically in 5 minutes an indication of the composition of the product or the additive level that is present. So any adjustments can be made basically immediately. The NIR method replaced wet methods that took a long time, sometimes an hour, sometimes longer, that had some safety issues associated with them, use of glassware, use of high temperature, hazardous solvents. So it's really a wonderful technology to be able to implant close to the manufacturing location, to be able to provide immediate feedback of process being okay or any possible upsets. So we have very successfully been able to quantitate plasticizer level and molecular weight for a number of products that are manufactured in the United States. Additionally, we have instruments to determine residual monomer. So we've replaced a GC method that was problematic and had to run 24 hours a day, and there were issues with that operation. We've correlated composition with impact modification level and performance. We've looked at reactions such as condensation, curing, and for products that are manufactured from natural products, such as soybeans, we've been able to determine 5 properties simultaneously through one measurement, and also determine year-to-year variations that accounted for needed modifications in the process. So NIR is really wonderful technology as long as you get past the required time expenditure to calibrate the system.
That's a really good point. Obviously, you have to put some upfront, time investment, for the measurements, to build in the model, do the calibration. But once it's implemented, it's a green technique. It's a replacement of a lot of method. And it's you can do both online and offline and inline, right? So wonderful. I really appreciate you share all those information with us. So, Chris?
Well, let's kick things up to a little bit of higher energy, and let's go over to X-ray. Pierre, you have 3 different X-ray techniques in your toolbox: XRF, XRD, and XPS. Although they all bear the term X-ray in their name, there are some real fundamental differences among those different products. Can you please give us a high-level overview on each of the techniques and how they fit in your polymer characterization? And what type of information can you extract from each of these different techniques?
Sure, Chris. And yes, you're correct. They all bear the name X-rays, but they're quite different in how they operate and what they get you. So maybe let's start with X-ray fluorescence. As mentioned, it's a bulk elemental analysis technique. Basically, the principle is relatively simple. It's you're shining high-power X-rays on your sample that we call primary X-rays. And what we're looking for are those secondary X-rays that get generated in the sample itself. And those secondary X-rays are going to have energies that are characteristic of the atoms present in your material. And typically XRF, depending on the configuration, the lightest element that you can possibly reach is actually boron. So for glass manufacturing, something of importance. For the polymer field of interest is anything that starts, I would say, minimum at least at sodium, and sometimes, depending on your application, if you can do a little lighter, fluorine, oxygen, carbon could also be useful. So the application typically in the polymer field, the plastic industry, is 2 big themes, I would say. Is you're either looking at trace metal contamination, and you want to understand why a part has degraded, or make sure that your production is within specification, so kind of a QC support type aspect. Or for R&D or even production, it would also be not trace, but like more additives put in the plastic to improve its property, its longevity, or modify some of the color or processing aspects. So there is also kind of a control where you want to be able to measure the different materials down possibly to low, medium, low levels up to percent levels, depending on what you're doing with it. So it's a very, very useful technique, heavily used for us, both R&D, QC support, and also kind of, as Dana was mentioning, for the IR, often an entry-level technique in conjunction with IR, because now you can also capture all the fingerprinting, at least for the inorganic part of your material. The other technique that we have in our laboratories comes through different names. So it's X-ray diffraction, kind of known in that field for inorganic people. In the polymer field, soft material typically referred as wide-angle X-ray scattering. And there are different subtleties on how you use the technique for those two different fields. But basically, the idea is that with X-ray diffraction or wax, you're going to be able to probe crystal phases in your material. And that could be related to polymer itself or to inorganic materials in the polymer matrix. Sister techniques I want to briefly touch on called small angle X-ray scattering. So wide angle, as it speaks, you're looking at large angle. Small angle, you're looking at angles that would typically between the incident beam and a few degrees at most. And there will be application for the polymer field, and I'll touch base on that. And you see even more application now coming from techniques called ultra small angle X-ray scattering, which is even a smaller angle where you start looking at larger objects. Basically, when you're talking scattering, there is an inverse relation between angle and the size of the object, and that's directly dictated by what we call the Bragg law. The interatomic spacing in the crystal phases are inversely related to the angle to which they're scattered or diffracted. As it was mentioned before, one of the pre-level analysis you do by X-ray diffraction or wide-angle X-ray scattering is basically phase identification. So similar to vibrational spectroscopies, database have been developed specifically more for the polymer soft material or organic molecules material. There are two big ones out there. I'll mention the one edited by ICDD, International Center for Diffraction Data, but there's also the Cambridge database that deal with polymer phasing and organic materials in general. So doing a phase identification, if you collect your data, is just a matter of minutes now with modern X-ray diffraction system. Phase identification is extremely rapid as well. Just a matter of minutes. Or if you're familiar with your material, you're going to recognize right away what you're looking at. And then beyond that, in the polymer field, so looking at what crystal phase you have, the big question is usually around like crystallinity, how crystalline is my material. So you're talking semi-crystalline polymer, looking at crystallite size, and possibly, depending on what the part you receive, it's like, could it have some orientation? Or, as was mentioned with the vibrational technique, you can also do now micro diffraction. So looking at small defect in your material and try to identify, or like possible phase blend that have somewhat phase separated. And if you want to get a little more information about what the phase separation is about, those are techniques that also can be used for that. Briefly going back to small angle X-ray, it brings an additional layer of information regarding, I would say, the size of the crystals. In the polymer field, the way the crystals are built is that you start from a unit cell, so similar to inorganic material, but those unit cells assemble into what we call lamellae. So they would be kind of like disc or rectangular type crystals. And it's really of interest to understand the size of that stack of crystal of unit cells, like how thick it is, how big it is. So small angle allow you to, through the measurement of the long period and the extraction of what is called the lamellae thickness, to get an idea about those dimensions. And going briefly to the other aspect, which was ultra small angle X-ray scattering, those techniques allow you to look at even bigger objects. So now you're past the lamellae size, and you might be looking at possibly particles, inorganic, or even could be like a polymer latex if you want to look at the size and the shape of your latex in your solution. That ultra small angle would be useful for that. Using a model for spherical particles, you can extract a particle size and a distribution out of that as well. But it could also be used in a sense if you're trying to get some information about what is the shape of your object. You kind of try to fit your signal to different models and figure out, are you dealing with sphere or are you dealing with cylinders if you have nanotubes or small fiber in your system? So I think that I'll move on to the other technique that we have in our laboratory that I'm in charge of, and that's called X-ray photoelectron spectroscopy. In the field, it's also known as electron spectroscopy for chemical analysis. So the same techniques bear two names, and that's a very surface-sensitive techniques. Once again, with that technique, you start with X-rays. You're shining on your sample. But what you're going to be doing here is actually you bring enough energy that you are extracting electrons from the material, from the sample surface through the photoelectric process. So you're extracting those electrons, sending them in your spectrometer, and what is of interest is to measure their kinetic energy, because you can actually relate that to their binding energy. So now, by measuring that energy, you can get some information. Did that electron came from a carbon atom or an oxygen atom, or was it silicon or titanium, iron, or etc.? So it's a very powerful technique. It allows you to identify pretty much any elements in a periodic table. There are just hydrogen and helium, the first two that cannot be done. But any other elements can be identified and quantified, similar to what an XRF would do for the bulk. Now the XPS is going to do that work for you for the surface. Because you're looking at electrons and they don't travel very far in a material, you're extremely surface sensitive, so like top 5 to 10 nanometer of the sample surface. But I was mentioning binding energy and the fact that we are looking at those energies. Actually, you get a chance now to know, okay, I know I have an electron that came from carbon, but I can even extract some information. Was that carbon involved in an alkyl bond? Was it an ester bond, or was it an alkoxy or a carbonyl bond? And you can extrapolate that to silicon. Am I looking at silica or silicate, or is that a silicon PDMS type material or things like that, siloxane? So the same that you did for the element, you can also quantify your chemical functions. So in organic polymer field, anything in a polymer matrix, if you have like additives that are intended to migrate to the surface, or maybe that did migrate to the surface not in a desired fashion, it's actually something you can look at, evaluate, and quantify. And I would say in a way that maybe other techniques would actually be completely blind to that fact. XPS is so surface sensitive, you can actually get information that would be missed by other techniques. So kind of in a nutshell, that's how we operate XRF, bulk elemental analysis technique, XRD, wide angle, small angle, crystal phase characterization, crystallinity, crystallite size, orientation, and other aspects where you can play also with temperature stage, and then XPS or SK for surface analysis, elemental quantification, and chemical function quantification.
Great. That's a lot to digest, but it's a lot of information and good information. The overarching objective for polymer characterization is to improve certain properties or attributes of materials being analyzed. You brought up crystallinity analysis earlier. How does crystallinity, crystallite size, polymorphism influence positively and negatively the characteristics you're trying to develop?
Right. So as we discussed crystallinity, it is usually with phase identification, it's one of the big questions asked. So what is the crystallinity in my material that I made or that I process in a certain way? Can you tell me a little more about that crystallinity, the crystallite size? So that's where we would, so those questions clearly would focus more on the X-ray diffraction, wide angle, X-ray scattering, as well as small angle, because you get information for those lamellae. So the way it would impact, obviously, the higher the crystallinity, the stronger the pad is going to be, the less flexible, more brittle. So we want to know that type of temperature. But other aspect that it would influence is it could be if you're developing a film or larger film for barrier properties, having a higher crystallinity is actually thought to help with slowing down diffusion of oxygen, for example, through the polymer film. The small angle would be useful as it would bring you additional information again about those lamellae dimension, in particular the lamellae thickness. And the interest of that particular measurement is that it is known to impact the melting points of polymer. So like you can then start correlating that to other data point you would have from other techniques, thermal techniques in particular. But beyond the fact that they impact mechanical properties, they can also tell you something about the way you processed your material. So the crystallinity and crystallite size, lamellar thickness, you're going to start figuring out, okay, did we spend enough time when we are molding that part? Do we need to annihilate to change this crystallinity? Or if we are looking at a high crystallinity, whether something that changed in the process, or if we're trying to support our customers, can we tell them, well, we think that you should probably operate at a slightly higher temperature to kind of help develop the crystallinity. We're talking a little bit about crystal phases, polymorphism. So the same material, same polymer could have a different crystallization behavior, could have different phases. Some of our polymers of interest can have piezoelectric properties and that have valuable application. So like one of the questions we get is like, okay, we made that part, can we verify that it is that particular polymer that we actually produced in that process, and did we make enough of it that it will actually behave as a good piezoelectric material. And in terms of, again, going back a little bit to processing, again, having the X-ray, the wide-angle X-ray scattering technique, XRD, now in combination with a temperature stage, it brings an additional layer of interest, because you can actually help support process development by understanding, okay, so if we take our polymer to a certain temperature, how long will it take to develop a certain crystallinity? Are we running into a phase transition that maybe you would want or not want? And how is that going to affect the crystallization behavior once your part is cooling back? One of the things we look for processing or even for 3D printing is part shrinkage. How do we understand that when you 3D print something, how can you control the amount of shrinkage you're observing, and how does it relate to the crystallinity or the time it takes to process the material or cool it down or things like that. And even though we're operating a lot in the polymer world, we're also looking at inorganic materials. Obviously, one of the big traditional questions in the polymer field is like, titanium dioxide is used as a pigment. It makes white. It also has UV protection properties, but you want to make sure you're using the correct polymorph of the TiO2. So rutile is desired. Anatase is absolutely to be avoided because it accelerates polymer degradation. So those are the type of things that XRD wax can answer very easily, very quickly. And also, if you added TiO2, it's totally possible to do quantification analysis. So that would be complementary to XRF. And look at by different technique for quantification XRD, the reference intensity ratio, or preferably a read-vert refinement could also lead you to figure out what is the concentration of the inorganic additives in your polymer matrix. So those are kind of different examples. I haven't mentioned looking at polymer orientation as well, but if you're doing with parts that have been processed in different ways, or fibers, filaments, and that you want to get some idea about orientation, it's possible definitely to do with a 0D or 1D detector. It's just a little easier to also do that with a 2D detector, because now you get a full picture, if I may say, of those Debye rings, so you can quickly assess if you have presence of orientation. So kind of in a nutshell, and focusing more on the polymer field as applied with X-ray diffractions, where you can have a lot of use out of it.
Oh, thanks, Pierre. I think that's, again, it's a really good summary about how X-ray techniques, XRD in particular, for example, in the polymer characterization, especially crystallinity, polymorphism, right? But that does bring up a very interesting question. I think that's not unique to, to you guys or to us. For example, last year, the past couple of years, we ran a collaboration with a university, on using multiple analytical techniques for the crystallinity study. It's a good problem to have. You have different techniques to study, one aspect of characterization. We use Raman. We know Raman is also a very sensitive technique to study crystallinity and polymorphism. The question then become, okay, how do you correlate the data? Maybe you or Dana, you guys want to comment? When you have two different techniques for one aspect of characterization, sometimes data, do agree with each other. Sometimes they don't. How do you correlate? If they don't agree with each other, how do you reconcile that data to make sense of that data?
So I'll start and turn it over to Pierre afterwards. We have used Raman to look at crystallinity in polymers. But I will have to say that, at least in my mind, the gold standard is X-ray diffraction. And so any data that we gather has to correlate with the X-ray diffraction data, because that's basically the most rigorous way of asserting crystallinity and structure from there. So Pierre can comment if he agrees or disagrees with my assessment.
I agree. I mean, Dana and I like X-ray diffraction, but I want to add that, when we compare techniques, and we do that, I mean, we are currently in the process of doing that on different projects, that we need to keep in mind that they probe different depths, they probe different sizes, and that they're complementary in a way that, I mentioned very briefly that by XRD we can do micro diffraction. On a commercial lab instrument, you'll get down to about 100 micron in size. Compared to a Raman, I believe, can do the same type of measurement at a 1 to 2 micron size. So for X-ray to be able to reach those very, very small size, I mean, you're talking going to probably a synchrotron beamline, which can be done, but it's not going to be done on a routine basis. So I see them to be complementary. You may sometimes get different answer, and I think it's based essentially on the fact that we are usually looking at different size scale. But if the material is homogeneous, and so that by Raman, Dana looking at a few micron spot with a Raman, and then a diffraction wide angle system looking typically, we're running a larger sample volume anyway to get a more average response from that particular material. And what we found is again, if the material is homogeneous, we have agreement between the two techniques. And then if you don't, then it might become interesting and dig a little more as to why. Is that due to the material, or is there something we need to dig further on the analytical approach?
Yeah, no, that's a great point, right? I mean, if you look at, if I'm using a very gross, simplified characterization, what we consider a bulk technique. You're looking at a larger sample volume, large crystal size, average property, if you will. Whereas Raman, especially with Raman microscopy, you are really looking at a single digit micron or even sub-micron, 750 nanometer, for example. So yeah, that's a very important, perspective. That's kind of how we feel. When you have multiple techniques, you got to apply the basic principle, trying to correlate the data, but more importantly, reconcile the data when there's a substantial difference. I appreciate that perspective. I think this is a perfect time we bring Sarah into this discussion, right? Because we know rheology has been used to study the crystallization of many polymeric systems as well. So, we've heard Dana's perspective from vibrational spectroscopy, especially Raman, but also Pierre's perspective using X-ray techniques for crystallinity study. So, Sarah, maybe you can share with us what unique information can rheology bring into the crystallization study? I know there's a lot of study out there, right? So maybe you can, give us your perspective.
Yeah, thanks, Rui, for the nice transition. As you say, the rheology is commonly used to monitor crystallization kinetics of polymers, particularly semi-crystalline polymers. That's quite obvious since we can control the temperature and observe a polymer cooling down from a liquid melt state to a solid. Even more, we can apply shear and strain to mimic the real processing conditions, so we can monitor the material response in greater details that way. So back to your question, compared to the other two techniques, rheometry doesn't enable a direct measurements of crystallinity structure or polymorphs, as like Dana and Pierre were describing. Instead, we do more of an indirect measurements of how the viscoelastic response of the material change due to the polymer structure. So this link between the flow behavior and the structure is unique to each chemistry and each polymer. And in that regard, so we can provide a specific structure property performance information that can help in identifying processing windows and predicting optimal condition for the production. So in that regard, I think it's a really unique technique and gives unique information. But it is also important to keep in mind that rheology is not simply a technique for measuring viscosity. It can be much more complex than that. So I would say that dynamic oscillatory shear testing is what gives us the most comprehensive information about the polymer at the molecular level. During a small angle oscillatory experiment, for example, we can monitor the evolution of a moduli. Since we're talking about crystallization in particular, we can measure the liquid-solid transition, or we can measure gel point, or simply follow the nucleation and growth process during an isothermal crystallization experiment, and much more. We can really think about a variety of different experiments to mimic better our process. So in short, the power of rheology is that I think we can relate these bulk properties of how the polymer stiffen, for example, which is a simple experimental observation, to a much deeper fundamental understanding of the material in terms of structure and performance. And to me, that's the fascinating part of the rheology science. However, rheology alone does not give us all the answers that we need. So, of course, it's very important that we complement the data that we get from rheology with the spectroscopy techniques, such as IR, Raman, X-ray, and many other techniques. So it's absolutely necessary to understand the why. I think Pierre was talking about the why. Oftentimes, we can't really understand the full pictures with only one technique. So for better understanding the why of those mechanical properties that we observe via rheology, we absolutely need to combine and complement with spectroscopy techniques, for example.
It's an excellent point, Sarah. Rheology is really a dynamic analysis as opposed to a static analysis. And if you look at the entire field of polymer characterization, we generally try to frame that into 5 major buckets: molecular mass and structure, morphology, thermal, as well as mechanical properties. Where would you say rheology fits into that scheme?
Yeah, interesting question. Thanks, Steve, for that. Well, I believe that rheology is the science that combines all these elements. And that's why the interpretation of something as an apparently simple flow curves can be extremely difficult. If we only look at the complexity and variety of the rheological behavior of polymer melts, for example, versus rheology of dispersions or colloids, or, for example, the transient viscosity measurements done by extensional rheology, we quickly realize that there is a wide spectrum of properties that we can probe under totally different temperatures, concentrations, and shear conditions. So my answer is that rheology, in my opinion, can be used to probe and correlate those 5 pillars that you have been mentioning, being that molar mass, structure, morphology, thermal and mechanical properties. As a matter of fact, thanks to great minds, starting from the ancient Greeks to all the mathematicians, physicists, and all the scientists that developed the concept of rheology early in the 20th century, we have today a huge number of theoretical models that can be used to extrapolate those pillars, that can be used to extrapolate molecular weight, polydispersity index, entanglement, molar mass, in general, structural information. Still, though, there are many rheological behaviors that are not fully explained, and it can only be fitted by the very best semi-empirical or empirical model. So that's so difficult this science can be. So if we look at the mechanical properties, then rheometry is based on stress and strain measurements that can translate it into material internal friction. So it's really amazing how we can observe that the bulk mechanical properties are in fact a reflection of structural differences at the molecular level. And as you said, the oscillatory tests are the best techniques to probe those molecular structures. So again, rheology is connecting those 5 buckets together, and to me, they are all part of the same puzzle, if you want.
Excellent information. When we think of rheology as the measurement of a material's viscoelastic behavior and how it deforms when exposed to different shear, temperature, or chemical conditions, I know you and Dana have been working with a hyphenated rheometer FTIR instrument where one can simultaneously analyze rheological and spectroscopic properties as materials go through thermal or shear-induced changes. Can you or Dana comment on the benefits of this technique?
Thanks, Steve, for bringing this up. Dan has been a big proponent of exploring the ReIR couple system. So I'm going just to give my opinion, and then if Dana wants to add some more, I would really appreciate that. So I should say that it's really amazing to see how many new avenues of interpretation this technology offered us. We have been working with the ReIR couple system for about 2 years now. We started to explore crystallization mechanisms and specifically some rheological behavior that can be correlated with the presence of intermediate structure. So we can now follow the evolution of the rheological profile during the crystallization and assign those rheological values to a specific change in the IR band, for example. So because of that, we realized that the mechanism of nucleation and growth that are involved in our material are often much more complex than what we thought. So a lot of good learning came from synchronizing and combining those two powerful techniques together. Another example where the couple ReIR technique has been key for us was to study the shear sensitive materials, where we wanted to identify the root cause of an anomalous rheological behavior, for example, observed under high shear. So these kind of studies can really help our chemists to redefine their formulations, since we have now a more clear understanding of the chemical and structural changes that are responsible for those odd rheological behavior under those particular shear conditions or temperature conditions. So those are only two examples, but we are also looking into other studies involving reactive chemistry and shear-induced crystallization. Together with Pierre, we are doing more studies on those regards, where the hyphenated technologies, in this case the ReIR, can clearly offer a unique advantage for interpretation and a better understanding of the why, again, of what we observe. So again, the presence of intermediate and temporary structures is very difficult to catch and characterize without any in situ measurements, because basically they are out of equilibrium events and they can only be captured through a dynamic type of testing, such like the ReIR system.
So just to add to what Sarah said, we are very excited to have this new capability and to be able to explore so many technical avenues that were basically closed before, because you ran a rheological experiment and you ran IR. Even if you did run IR at high temperature in a heated cell, it was not the same thing. And so we believe we are going to have many years of benefits and very interesting science ahead of us with this new capability.
Yeah, no, I just want to chime in here as well. I mean, I want to echo what Sarah and Dana mentioned, right? What we found particularly useful is to capture, that transition state, the metastable state, the intermediate state. You wouldn't be able to do otherwise. It's when you do that in a sequential manner, you lose fidelity. You might get a start state and end state, but you lose the detail in the middle. From our perspective, that's where we see the biggest benefit, of this hyphenation technique.
And I see that we experience exactly the same thing. That's really the benefit that brings to us this hyphenated technique. And so we're looking forward to studying more systems.
So in a way, it's like doing kinetics with just the data at the very beginning of the reaction, at the end of the reaction, 2 points, and nothing in between, which is basically a sequential experiment. So now we can explore the entire time domain in which things happen. So we are very excited.
That kind of brings me to my last question, right? Have you ever been able to compare the sequential analysis to doing two separate tests?
Yeah, I would say that is part of our job, to look at different techniques and stitch together the information collected before and after an event. That could be chemical reaction or a change in process. So yeah, we absolutely do that. Dara, do you want to add something? I mean, now because of the RHEO-IR, we do have an in situ technique that can mimic the stress temperature used in the processing. And at the same time, we can look at the structural and flow data in real-time dynamics, just like Louis emphasized. This is absolutely not possible to do with any sequential analysis. I should also add that the RHEO-IR is not something that we run as a routine test at Arkema. I wouldn't consider this a QC tool for us. This is truly a research tool to shed light on difficult questions, such as changes in order, chemistry, and other structural modifications that are occurring during material processing. In our case, we have a number of applications where understanding of the subtle differences in chemistry and processing is critical. And usually that's true for more demanding manufacturing industries where such subtle differences can have a huge impact on performance or even profitability, because you can sell the material for a larger margin. So thanks, I think that's a really good point, and thanks for giving the opportunity to talk about this today.
I totally agree. We are looking at many years of very interesting science that we plan on doing.
No, absolutely. And one more point I want to make about this hyphenated technique, right? And obviously, you guys are working with this rheology FTIR combination or hyphenation. You're probably aware of this. We also have this rheology with ramen, that different hyphenation. We actually did some very interesting study through some collaboration. Well, one thing, for example, early on we talk about one of the very strong application area for ramen is polymorphism. In one of the studies we actually find one of the very rarely observed transitional state, one of the polymorph, form. It's very difficult to catch because of the conditions. Through this dynamic experiment, we were able to catch that, and we were able to, have a better understanding about the overall process. So yeah, no, I absolutely with everyone that, the combination is not a QA/QC tool. It's not for routine use. However, combination of the two techniques really unleash a great power for better understanding, holistic understanding, not only the property, but the process that take the material to get to that property. So, that's a really great perspective, everyone. I really appreciate your time and share with us all, your expertise. Before I wrap up, anybody else has any question or comments?
Well, we'd like to thank you for inviting us to participate in this podcast. And we are delighted and hope it's going to be of interest.
Well, it will. I'll assure you this is, your perspective, many years of experience, different aspects, different techniques, how we put them together, how we solve the mystery, it's going to be a great value for many people in the field. So with that, I would like to thank you all again for your time and your willingness to work with us. It's very much appreciated. With that, it's a wrap.